Now, as we start topic 4 of chapter 2, we're going to take a look at linear inequalities now and problem solving. So, they give you a little example, but what we want to do for background is to identify these inequality symbols. Some of you may know them already. This is less than or equal to, greater than or equal to. So they're used in replacing what used to be an equal sign. We're using this inequality sign. And then we're going to give you some more background here shortly. Now, the standard form of the inequality, the linear inequality, is very similar to what we had before. AX plus B is, let's say, less than C. The standard form of the linear equation was we had an equal sign here. Now we're having an inequality sign. So when we illustrate the value of what our x will be, it's no longer just one value, but a whole series of values. So for instance, if we were to say that x is greater than, let's say, 2, how would you put that on a number line? Well, here's the number line. We're interested in 2. Now, we're saying that x is greater than 2. So 2 is not included in that set of numbers. Now, in the old days, we used to put like a little hollow around 2 and then darken the area to the right since it was greater. So we would graph it this way. Well, it's hard to put little circles when you are using the computer. So we've modified that now to, when it says x is greater than 2, we put a parenthesis at 2. And this is what it will look like in your homework log. We're not going to use the hollow circle to indicate that 2 is not in the set. So that's what this indicates. So this was x is greater than 2. Now, students often get the lines and the direction of the lines mixed up. If you have it in this form, notice the point of our inequality sign is the direction the arrow will go in. All right. Now, something else that goes along with this is what we call interval notation. We have set builder, we have exponential notation, we have roster notation, and now interval notation. Well, if you have the graph correct, then you can take interval notation right from the graph. We're going to put a parenthesis, and we're going to put 2. So this translates to this in interval notation. And then this is going out here to positive infinity, so we put it there. Positive infinity, that's where it's going. And infinity, whether it's negative infinity or positive infinity, always has a parenthesis associated with it. That is what interval notation is. And we'll show you the others as we go along. Now, a modification of this is if you have x is greater or equal to 2. Now, we used to graph that on a number line by putting a dark circle, filled in circle over the 2 to indicate that the 2 was included. Now when we graph it, we're going to put, instead of a dark circle or a parenthesis, we now put a bracket. So the bracket is the symbol to indicate that 2 is included in the set, and then the point tells us the direction we're going to darken. Now to put that in interval notation, again, right from the graph, we use a bracket, we use 2, comma, it's going to infinity, and as we said, infinity always has a parenthesis. Now in your textbook, they give you this summary. This is what we call set builder notation, where you have a brace. X is such that X now is less than A. So you're going to put A on the number line, and since it's less than that and not including it, you use the parenthesis, goes off to the left now. Notice the direction of the point toward the left, and in interval notation it's coming from negative infinity up to, in this case, letter A, and then a parenthesis. If we flip the sign and it's greater than, the parenthesis faces to the right. If A is included in the set, less than, it's a bracket to the left. If it's greater than or equal to A, it's a bracket to the right, and interval notation follows. Now another one while we're here is if you have set builder notation looks like so. X is such that A is less than X, and X is less than B. Again, A and B are on the number line, and since they're only less than, it's going to be a parenthesis facing right this way, parenthesis facing left this way. And there is your interval notation right from the graph. And if it's equal to, it's brackets. If one is greater than or equal to or whatever, that would be a bracket, and then this one's only a parenthesis. So it gives you a nice little summary of this, and probably should be included in your notes. And to wind up our concept check, background, what's wrong with this? Let me pause. Yes, we just finished saying that infinity is always a parenthesis and never a bracket. Okay, they want us in example 1 using set builder notation to graph these on a number line. So the number we're interested in is 2 for letter A. It's greater than or equal to, so we're going to use a bracket. And the arrow points to this direction, and then putting it in interval notation. Now here, the number we're interested in is -1, and it's showing that the arrow is going to point to the left. It's not equal to, so we use a parenthesis and interval notation. Now this is a compound inequality. X is in the middle, so the number we're interested on the left is 0.5. On the right is a 3. Notice this one has an equal sign, so this one has a bracket. This one has a parenthesis. Fill it in, and right from the graph, you can do your interval notation. Now, when we are solving linear inequalities, we use the same properties in general. There's one exception, we'll get to that shortly, that we use in solving equations. So let's move on. So we can add something to both sides, and it's still fine. So let's do example 2. Now, if we want to isolate the x, we can transpose, or we can use the other technique of adding 2 here, adding 2 there. Here the 2's cancel out, and we get x is less than 7. So 7 is the number we're interested in, and it's only less than 7, so 7 is not included. So we put a parenthesis, and notice the arrow is pointing to the left, and putting that in interval notation looks like so. For example 3, we see this is our example. Again, we want to get all our x's over to one side. So transposing it, it becomes a negative 2x. So this is just going to be an x left there. To get rid of the 4, we'll transpose it. It becomes a negative 4, and a negative 6 is a negative 10. To graph it, negative 10, and we're going to use a bracket here. I said negative 10, I put a 3, but negative 10, a bracket, notice the direction of the arrow, and then interval notation, bracket, negative 10, comma, infinity always has a parenthesis. So with adding something or subtracting something from both sides, there's no problem there. But we're going to show you where the one difference occurs. If I write this, 2 is less than 4, that's true. And if I multiply the 2 and the 4 by 2, I now get 4 is less than 8. That is still true. But how about if I used a negative? Now this is a negative 4 and a negative 8. And now we find that negative 4 is not less than a negative 8. So the rule that comes out of this, because this is not true this way, if you multiply something by a negative in an inequality, or divide by a negative, in order to keep it true, you have to reverse the direction of your inequality sign. It's going to go from less than to greater than. This, put a little star in your notes. This is what they're describing here. So, when you're dealing with an inequality, and you're multiplying one side, and then of course the other, by a negative, for whatever reason, you have to reverse the direction of our inequality sign to keep the statement true. And here in the textbook they're describing it. All right, so let's take a look at example 4 as I set it up. Now in example 4a, we've set it up. We want to isolate the x. And in a situation like this, we would just use the reciprocal. 4 over 1. 4 over 1. So here everything cancels out nicely. You're just left with the x. We're not dividing or multiplying by a negative, so we don't change the direction of the sign. So here, 4 will go into there once, 4 will go into there twice, so we have x now equals 3/2, which is what they have. And then plotting that on the number line, you're going to use a bracket, and the arrow is going to point to the left, and then writing that in interval notation is pretty straightforward right from the graph. Now let's look at letter B. To solve letter B, we're going to isolate the x by dividing both sides by a negative 2.3. But since we're dividing now by a negative, to keep this statement true, we must reverse the direction of our inequality sign. And a negative 2.3 goes into there a negative 3 times. So, graphing this now, there's our negative 3 right there. Well, it should be over here actually. And what do I use? A parenthesis or a bracket? Parenthesis or a bracket? Bracket. And it's going to go to the right. And interval notation, bracket, negative 3, comma, positive infinity. Remember, infinity is always with a parenthesis. And there's the solution, and they're really pointing out the reversal of the inequality sign because we're dividing by a negative. And then writing it in interval notation. In your textbook, they give you this series of steps again. If there is a fraction, get rid of the fractions. Get rid of grouping symbols. Combine like terms. Then transpose by adding or subtracting as needed to get all the letters on one side. Now here's where you really want to try to keep them positive, because if you're going to divide by a positive, then you don't have to worry about changing the direction of the inequality sign. But if you're dividing by a negative or multiplying by a negative, you must change the direction of the sign to keep your inequality true. And of course you can check it. Alright, now in example 5, it's a little bit tedious, but let's just follow what they're doing here, because we'll have plenty to work ourselves. So here we're going to just reverse the signs by removing the parentheses, and we get a negative 3 and a negative x, I should say, and a plus 3. This is plus 2. Here we distribute. Get this, get this. Now we collect like terms. Well, we have a negative x and a 5. 6x plus 1x is 7x minus 15. Okay. Now what we want to do is get all the x's over on one side. So we could add this x over here, transposing it, get 8x, add 15 to both sides, we get 20, and then divide by 8. And we get, when we simplify, 5 halves. Now, this is, I think, critical for many of you, because okay, following this through, in case I didn't pick up on it, lots of steps, and then eventually when you divide by 8, the x is on the left. Well, initially it's on the right, but we're going to move it, switch it all around, so the open side is toward the x. And it's much easier to then graph and put in interval notation. Again, if I didn't cover this, we want to go over it in some detail. And in interval notation and the graph. Remember, infinity is always with a parenthesis. All right, well, let's do number 6 in some detail. We'll write it up for you. So this includes a fraction. So how many terms do we have here? Well, this is all one term. This is a term. And this is a term. So 3 terms. Now with a fraction, as with equations, we're going to multiply each term by the lowest common denominator, which here, of course, is 5. So we multiply this term by 5, this term by 5, and this term by 5. Nice 5 there. Okay. So here the 5's cancel out. And that's why you want to multiply, to get rid of that fraction. So now we're going to distribute. That gives us 2x minus 12 is greater than or equal to, nothing to cancel out here, so this is 5x. Nothing to cancel out here, so this is a negative 5. Now, if I want the x to be positive, I'm going to bring this over to this side. So this becomes a 3x. And there's no x there. All right, now I'm going to bring this negative 5 over as a positive 5, and this gives me a negative 7. Now, the way they do it in the textbook, they moved this 5 to the other side, made it negative, as you see here. But now I'm going to divide by the coefficient of x, which is 3. But I'm dividing by a positive 3. So the 3's cancel out, and I get x now is less than or equal to a negative 7/3. Notice I get exactly the same thing, but here they had to divide by a negative and reverse the direction of that sign. So again, a benefit from having your variable positive, you don't have to worry about reversing the sign. By bringing this over to the other side, in a sense, we reverse the sign. Okay, now example 7 illustrates an inequality we get every once in a while. We're going to distribute, and we get this. But notice when we subtract out the x's, we get a true statement. 6 is greater than 1, but there's no x value anymore. Well, this type of equality is such that no matter what value you put here for the x or there for the x, it will always, as long as it's the same, will always be a true statement. So for this, the graph of it is all real numbers, and an interval notation is from negative infinity to positive infinity, and the graph is a solid line with arrows thickened on both ends. This is the graph of all real numbers. This is the interval notation of all real numbers. In our textbook, we sometimes have word problems that are inequalities. So they usually give us some key words. At least, at most, between, no more than, no less than. And that indicates you're going to be dealing with an inequality. All right, so let's take a look at this one. A salesperson earns $600 per month plus a commission of 20% of sales. Find the minimum amount of sales needed to receive a total income of at least $1,500 per month. All right, so they are getting $600. Then they're going to get 20% of their sales. Well, how much is that? Well, we don't know. We'll call that X. Now, they want to earn a minimum of $1,500. So we want this to be greater than or equal to $1,500. Now, we could leave the decimal because that's only one little calculation. So we're going to subtract 600 from both sides, and we get 0.20x is greater than or equal to 900. Now we're going to divide both sides by 0.20, and let's see what they get. And it would be, you would have to have equal to or greater than $4,500 in sales to guarantee this salary. Now in your textbook they go through it in much more detail. I gave you the short version. All right, let's look at example 9 now. It's finding the annual consumption. Now they're giving you a formula for this. This is something similar to what we're going to use in chapter 3 here shortly, where we have consumption is equal to the negative 9.4t plus this. And t is the number of years after 2000. So it's saying in the United States, use this formula to predict the year that the consumption of cigarettes will be less than 200 billion per year. Now, as we read this, we're basically going to substitute this information into our formula. So we want to find out what T is. So we're going to put the consumption of 200 billion where the C is, and you'll see that here. So the 200 is replacing the C. They put it in a little different order, and they're solving for T. Now notice you had to divide by a negative here. So they had to reverse the direction of that inequality, and they're getting 24.6. Well, if we started in the year 2000, and we just add 24.6 to it, so around 2024 or 2025. All right. And that winds us up. We'll move on to our mini lecture booklet.